All right, yo. So we are back with this malware walkthrough for the second lesson. So today, what we're going to do is we're going to go through in some detail through the code base. We are going to, just talk about it. I'm going to point out, some of the interesting parts, just to kind of help you guys understand what's going on here, so that you can use it. You can use it in your own shit, right? Okay, so as it stands, our malware is right now it's a stateful system agent, right? So it observes its environment, it records structured data, it reads, it reacts to failure, and it communicates, right? And so currently we're dealing with control flow, I/O, and state management, right? And which is exactly what most real malware actually consists of. So at a conceptual level, we're dealing with, we have 5 responsibilities right now in the malware, right? Configuration, identity, traversal and observation, decision making, which is intent, like we talked about, state reporting, or state recording, and reporting and artifacts, right? The Rust file is kind of organized to reflect this. Right now, you see it's even though it lives in a single source file, okay, it's organized. Later in the course, we're going to split this into modules. Right now, I just want the clarity, right? I just want you guys to be able to see this stuff, and then we will be kind of doing that refactor, okay? Now, so let's get into it. So up here first, we still have some constants, okay? So this is basically, think of this as this is stable identity, okay? And these define operational identity. Where the malware starts, where it lives, and where it leaves reports, right? And so there's nothing dynamic here yet. Eventually, what we're going to do is all of this is going to be dynamic configuration coming from the C2 server, right? And as far as Rust goes, const is a compile time constant, right? They're stored in read-only memory, there's 0 runtime allocation, and they're immutable by design. And also, man, these are kind of in here on purpose because these are very easy to reason about, and they're easy to detect, and they're easy to break, okay? And so, like I said, right, consider this early stage tooling. And so later we're going to evolve these and replace them with runtime configuration, pull them from memory, and eventually eliminate disk paths entirely, right? And it's just going to be and it's just going to be really between the malware and the C2 server, okay? So now feature flags. These are very important, okay? So feature flags, like right here. See, we got target hunt, we got FSEnum. I think that may be, and beacon, right? So so throughout the code, you're going to see these, okay? And so what these do is these provide runtime. These provide us with build time capability selection, okay? So this feature flags, dude, they're awesome, because the thing with feature flags, not only do they allow you to tailor your malware for your environment, right? So if you got a pretty robust piece of malware, but you get into a machine that you don't necessarily, like, dude, I don't need enumeration. Like, that's not what I'm doing right now. You can compile that binary without that enumeration feature, which is going to make your binary smaller, and it's going to eliminate a feature which could cause an issue. The leaner it is, the less likelihood of something going wrong internally. And another thing that's great about feature flags, your malware will not create the same hash, right? So if you do have a robust piece of malware and you turn these feature flags on and off, the hash is going to be different. And so this is really a way to kind of, basically this will make it so that it's very difficult for defenders to see if this malware is part of a malware family, right? So feature flags are very important. Okay, so let's move on to the finding struct. Yeah, right here. Okay, so this is basically the malware's internal state of memory of reality, right? We got this basically informs the malware and us as attackers through the C2 server. What did it touch? What was it? Did it succeed? Did it fail? Did it matter? What happened when we touched it? Right, all of that. So structs, these are named type records, right? And they're much safer. If you remember, we used a hash-based record before. And using structs is the way that you should go, right? They have compiler enforced correctness, and they provide clear serialization boundaries, right? Because you're clearly stating what is being serialized. And real malware, it almost always collects structured data, serializes it, and treats observations as a first-class state. Okay, and then on the defender side, this kind of mirrors EDR events, audit records, and behavioral telemetry. Okay. And so later on, we're going to add UIDs and PIDs to this and area codes and make it live in memory only. And we're also going to change how it's emitted, right, by using buffers and delays and encryption, right? Okay, so let's move on down to the crawl state. Okay, so here, this is what you would call, this is explicit state threading. Okay, we're not using globals, statics, or kind of relying on hidden side effects. We're passing mutability state explicitly. Okay, because VEC findings right here, right? This is owned growable memory. Okay, so these are borrowed mutably into functions. There's no shared mutable state here, so we don't get any race conditions. And honestly, guys, this is kind of how in Rust, how you write safe, recursive, and iterative scanners without fighting the borrow checker. Okay, so Rust requires you to be very honest about state. But yeah, so you could take this technique in here, and this is at the core of, you could implement all kinds of scanners with this technique. Okay, now. Timekeeping. So down here to the current timestamp. Okay. Timestamps are kind of, we're using them for the simulation here, really. They create temporal ordering, and so, we produce these timestamps at discover time, and so, as attackers, we do care about things like, sequence, delays, gaps, and of course boundaries. But these also allow defenders to reconstruct our timeline, right? And kind of see the different phases of our attack and also escalation attempts. And so we're gonna get rid of this. Next lesson, this is gone, right? This is gone. We will, this is bad OPSEC, right? We're not going to use timestamps after pretty much this last lesson. All right, so logging. Let's talk about the local logging first. So this mirrors an attacker mistake. Okay, you would not do this. Okay, consider this side effect logging, right? So you'll see here, open options. It provides append-only writes. We completely ignore failures. We do that intentionally because logging, it never crashes the program. So it's like whatever. But just like the timestamps, this is bad OPSEC, right? And that's the point. So for defenders, man, this is gold, obviously, right? Because if you remember in the last lesson, these artifacts single-handedly saved the AppArmor lab, right? Like, we used AppArmor, we got confinement, but we didn't get any visibility. And so then what we did was we scoured the system to see if any artifacts were left behind for the attacker, and we found something that was able to give us the visibility as defenders that we wanted. So in the future, man, like I said, this will also probably be the last time you will see this local logging, because this just makes defense too easy, and we want to move on in the defender section to introduce new tooling and things like that, and also more realistic late stage malware scenarios. Okay, Okay, so yeah, the target matching, right? So right here. So basically what this is doing is this is classification, right? So we're not just scanning shit, right? We're deciding what matters, okay? And so, we got pattern matching going on here, string normalization, and so, and this very much mirrors real malware because it searches by patterns and not path. But for defenders, this also surfaces intent. Okay, so it's a little bit of a double-edged sword when it for attacking. Okay, but in the future, this is all going to be coming from the C2 server, right? This is going to give us real-time configuration changes, which it's a lot of fun. It's a lot of fun. Okay, now let's go ahead and go down to file system traversal. Okay, so this is if you know your computer science, this is a breadth first search, right? So it's a bounded graph walk, and so you can see here we're using VecDeck VecDeck is very common in creating BFS and Rust, and then we're using PathBuff here for ownership. And we'll also see that we error handle here without any kind of panicking. And so this is where I guess you could say containment meets behavior, because if a read fails, the state changes, right? Denials don't crash, and or malware's behavior got an itch. Okay, and that's where the malware behavior adapts. The malware doesn't break, it learns. And that's important. This isn't some AI bullshit, right? But it's your malware is becoming smart. Okay. Now, so within here, let's talk about error handling, because I really talked a lot about about error handling. You'll see here that we have every file system access is wrapped in a match, right? So you'll see here is dir match, try open file match, right? And so so failures, like I keep saying, they should be expected. You shouldn't be surprised. They should not be exceptions, right? And so we're using Rust pattern matching here, along with which provides us very explicit and proper error handling. You can see here, we are very explicitly handling these errors. Okay. Later on, we're going to be suppressing failures entirely. We're also going to implement selective retrying. And by the time we're done, we will be using a completely different strategy. But that's kind of the direction that this section is going to go in. Okay, so the final section is the reporting section. Okay, and so guys, really, this is state emission. Okay, data exists and transport. Data exists first and transport is secondary. Okay, and you'll see here we're using SERDI for serialization, and we define explicit boundaries. Okay, and we have clear failure handling. Right, and also, guys, you got to remember, man, at its core, C2 really isn't anything special. It's really just I/O, because all the real logic is done upstream. And for defenders, this is producing signals, right? Because artifacts is a signal, and network is another signal. Utilizing the network for exfiltration. And then you'll see down here the main function, right? It doesn't do much, man. It handles coordination, and not blowing smoke up my ass, guys, but this is good design. Okay, when you see no interesting logic in main, that's kind of the hallmark of maintainable system code. All right, so that's pretty much it. So what's next, right? So what are we gonna do with this thing? All right, so I got a little list I've been keeping of things that I want to do. And so some of the things that we're going to do to this is we're going to be removing the disk artifacts entirely. We're going to move to in-memory execution for the malware. We're going to implement event-driven behavior, privilege escalation. We're going to get much better OPSEC. We're going to do telemetry suppression, runtime, C2-driven configuration. The next lesson is going to cover persistence And yeah, so lots of stuff, right? And right now, yeah, the code is very honest, I guess you could say. It's not clever. And you don't really want it to be clever. You don't want a gold plate here, right? You don't want, because you want these binaries to be small, and you want your features to be very targeted, okay? So cleverness will come later when we start trying to shake the fenders, okay? Now, also, it's important to recognize, I see the term malware and exploits kind of used interchangeably. And dude, that's not it. Like, malware is not exploits. It's really just state management and error handling and IO, right? And the code is a perfect example of that truth. And you know, one of the reasons that I chose to write this in Rust is because it honestly, it gives you a lot of things that you, when you write with C, that you have to kind of do yourself, right? The memory safety, explicit state, the honest control flow, and you know, these real system constraints. But yeah, so yeah, that's it, guys. If you have any questions about this stuff, hit me up. Hope this was useful to you. Use this to make your own stuff, and yeah, let's continue on the course, and you know, we'll evolve this stuff. Ask those respectable questions, get respectable answers, and yeah, I appreciate you guys, and I'll see you in the next one.